This is lecture 4D, and today we're going to talk about the ninth and final type of chemical reaction. This is a non-obvious type of reaction. It's an oxidation-reduction reaction that contains a strong oxidizing agent. So a couple of definitions to start. First, a reducing agent is a term we use to describe a reactant that causes another reactant to be reduced. Why would that be true? Because it is getting oxidized itself. So whatever gets oxidized in a chemical reaction, that reactant is causing another reactant to be reduced, so we call it a reducing agent. And anything that has a strong tendency to be oxidized, anything that has a strong tendency to lose electrons, will be a good reducing agent. So what would that be? Elemental metals, sodium, potassium, magnesium, those all have a strong tendency to give up electrons, so they get oxidized easily. So those would be good reducing agents. Industrially, elemental carbon is used as a reducing agent because it winds up reducing ions of metals into elemental form as the carbon gets oxidized into carbon dioxide. An oxidizing agent is the opposite. It's a reactant that causes another reactant to be oxidized, and it does that because it is the reactant that gets reduced. So if you can imagine what types of things have a strong tendency to gain electrons, those would be very active non-metals like halogens or oxygen. Those would be considered good oxidizing agents. We're going to look at 4 other oxidizing agents that are used quite a bit in general chemistry, even in organic chemistry: the dichromate ion, the permanganate ion, concentrated nitric acid, hydrogen peroxide. We're going to tell you what they do, and then if you ever recognize those in chemical reactions, that's going to be a good indication that an oxidation reduction reaction is going to occur, and we're going to show you how to predict the products for those reactions. So these 4 common oxidizing agents. The first one is the dichromate ion. Whenever it's involved in a chemical reaction, it actually causes other things to be oxidized, so it takes their electrons, and it actually turns into the chromium positive 3 ion. Now, why is this? If we do oxidation numbers in the dichromate ion itself, oxygen has an oxidation number of -2. There are 7 of them, so 7 times -2 is -14. So if we know the oxygens are -14, that means the chromiums have to account for an oxidation state totally of +12. So the 12 and -14 add up to the charge of that polyatomic ion, which is -2. Now, if the 2 chromiums add up to +12, each chromium must be +6. So this is the key number in this specific material. Chromium has a very high positive oxidation state. Anytime you have something with a really high positive charge, it's going to strongly attract electrons. And these chromium +6 ions attract 3 electrons each until they become a more manageable charge of +3. So because dichromate has a very strong tendency to do this, it's a strong oxidizing agent. The same thing's true for permanganate. If you have a permanganate ion and it's in an acidic solution, it will preferentially undergo reduction and turn into the manganese 2 ion. Why would that be? The oxygens in the permanganate ion each have an oxidation number of -2. There are 4 of them. They add up to -8. That means the manganese's oxidation state has to be +7. And that is such a high number. It's a strong attraction for electrons. It actually pulls in 5 electrons from whatever it can find to reduce its charge down to +2. So another strong oxidizing agent. If the permanganate ion is used in a basic solution, as it's getting reduced from +7 to +6 to +5 to +4, it will actually precipitate out at that point as the solid manganese 4 oxide. Here, the manganese is going from a charge of +7 to a charge of +4. It's still being reduced. It still has a strong tendency to do that. But once it creates this precipitate, it no longer gets reduced. So you don't form manganese 2 ions in basic solutions. You actually form the precipitate of manganese 4 oxide. If concentrated nitric acid is used in a chemical reaction, it undergoes a really interesting reaction where it actually turns into a poisonous orangish gas called nitrogen dioxide. In the nitric acid, the nitrogen has an oxidation state of +5. You can figure that out. The hydrogen is +1. Oxygens are -2 each. They add up to -6. So that means the nitrogen would have to be +5 to make them all add up to 0. And that's a high oxidation state. And in a very acidic solution, that nitrogen will pull in an extra electron, reduce its charge to +4, and create a little neutral molecule, NO2. Notice it's not the nitrite ion because there's no negative charge on it. It's NO2 without a charge. That's nitrogen dioxide. And then finally, one of the most common oxidizing agents is hydrogen peroxide. We use that all the time. We actually put it on cuts, right? Well, what hydrogen peroxide does is it has a strong tendency to turn into water because a peroxide ion is a special type of oxygen ion. It doesn't have its typical -2 charge. If you think about the oxidation number of the oxygen in the peroxide, well, hydrogens have to be +1. They can't be any higher than that. So if each hydrogen's a +1 and they add up to +2, the oxygens combined have to add up to -2, which means each oxygen is -1. Not an incredibly high number, but oxygen is way more stable as a -2 ion, and so hydrogen peroxides will scavenge electrons to try to allow the oxygen to gain an electron each to go down to a charge of -2 where water is formed. This is the reason we actually use it on cuts. You place hydrogen peroxide on a bacteria cell, then the hydrogen peroxide will oxidize a lot of the molecules in that bacteria cell. It destroys those molecules, therefore the bacteria is unable to do cellular activities or respiration, and the bacteria dies. So hydrogen peroxide actually kills bacteria due to the fact that it oxidizes the molecules in the bacteria cell and then kills them. So if you have a strong oxidizing agent in a reaction, what is it going to oxidize? It's going to oxidize anything it can take electrons from. So the most obvious candidate at first would be if you have any elemental metals, because elemental metals tend to lose electrons anyway. So if you have metals with a charge of 0, they're in their elemental state, an oxidizing agent can pull their electrons off and they'll create their commonly formed positive ion. Or if you have a transition metal or a p sublevel metal that actually can form multiple charged ions, if you have a metal in a low charge as an ion, you could actually oxidize it to a higher charge, and we'll see some examples of that a little bit later today. Now, the p sublevel metals, I would expect you to know what possible ion charges they make. That was back on test 1. They either lose all of their outer shell electrons or they only lose their p electrons, giving them 2 possible ionic charges. The transition metals, we were way more general. We just said, well, they form multiple ion charges. You're not going to know what they are, but there's 3 elements that are in the transition block on the periodic table that I would like you to know what their common charges are. Iron, copper, and mercury all can be in their elemental state with charges of 0, but I would like you to know that the 2 ions that iron atoms will form when they lose electrons are +2 and +3 ions. Copper atoms only form +1 and +2 ions when they lose electrons, and mercury forms +1 and +2 as well. So we'll see instances where either you may have elemental metals like mercury 0, copper 0, or iron 0, and they'll get oxidized up to 2 or 3, up to 1 or 2, or up to 1 or 2. Or if you have iron, copper, and mercury in these intermediate oxidation states, an oxidizing agent can oxidize them up to their higher charge. Another type of substance that an oxidizing agent can oxidize is a nonmetal anion. If you have something like a chloride ion or a sulfide ion or a phosphide ion, they all have octet configurations. They're fairly stable. But if you can have some substance have a greater attraction for those excess electrons they have, you can turn them back to their elemental state. So oxidizing agents can cause chloride ions to turn back into diatomic chlorine. They could cause sulfide ions to turn back into elemental sulfur, which sulfur in its elemental state exists as S8 rings, or phosphide ions to turn back into elemental phosphorus, which in its elemental state exists as P4 molecules. The final thing you're going to see quite often is if you ever have an ITE ion, like a nitrite or a sulfite ion in a solution, those can be oxidized into AT ions. So nitrite can be oxidized into nitrate, and that's because the nitrite ion, nitrogen has a lower than its maximum oxidation state. Here in the nitrite ion, the O's are -2 each. They add up to -4. The nitrogen would be +3. If you switch it to an ATE ion, now the oxygens add up to -6, so the nitrogen is a higher oxidation state of +5. So ITE ions are another candidate to be oxidized up to 8 ions. So let's see if we can practice today how to predict products of chemical reactions that have known oxidizing agents in them and show you how you do this. First example, let's say a solution of potassium dichromate and tin 2 nitrate are mixed. Now, if you look at this, this is two compounds. The first thing you should do is think about switching the partners and looking for an obvious exchange reaction that forms either a precipitate, water, or a gas. If we switch the partners, these would be the two products. The first one, potassium nitrate, has an alkali metal ion in its formula, and the first solubility rule says alkali metal ions never precipitate with anything, so that's not a precipitate. We actually don't have any rules that tell us about tin ions or dichromate ions, so if you don't have a rule concerning that, you can't assume it would precipitate. You'd have to assume it doesn't. So it looks like there's no precipitate here, no water formed, and I could have also written no gas formed. So if that doesn't happen, that means this is a non-obvious reaction. So the products were wrong, erase those, and when you have a non-obvious reaction taking place, you go to Plan 9 from outer space, which is write the reactants in ionic form and look for a non-obvious reaction. So for our reactants, I'm going to write the potassium dichromate as a potassium ion and a dichromate ion. And we saw this on an earlier homework. When you're doing the Plan 9, even though this dissociates into stoichiometrically 2 potassium ions and 1 dichromate ion, doing Plan 9, you only want to know what the ions are in the solution. Doesn't matter how many there are. So I'm only listing the 2 ions that come from potassium dichromate. And for the tin 2 nitrate, I'm going to do the same thing. I'm producing tin 2 ions and I'm producing nitrate ions. Stoichiometrically, there'd be 2 nitrates, but that's not important here. So I'm just going to write each of the ions that exist. Now, we learned last time that a non-obvious reaction that could exist is a Bronsted acid-base reaction. But you'd have to have an acid and a base here. And acids have hydrogens in their formula, and there certainly is no acid here because there's nothing with a hydrogen, so it can't be that. But whether you recognize that or not, if you ever see in your reactants one of the strong oxidizing agents we've talked about, and there is, in this particular reaction, a dichromate ion present, then that means you're going to predict it's going to be a non-obvious oxidation reduction reaction. So the reactants contain a strong oxidizing agent, and the way you predict the products is by calculating the oxidation numbers of all the elements in the equation. And here's what we're going to do with that. Okay, we look for an element whose oxidation number can go up and another element whose oxidation number can go down. So first, the potassium ion has an oxidation state equal to its charge of +1. In dichromate, the oxygens are -2. The chromium has to work out to +6. We did that earlier. The tin 2 ion would have an oxidation state of +2. And in the nitrate ion, the O's are -2 each. They add up to -6. So the nitrogen would have to be 5, so that 5 and -6 add up to -1. So when we have a reaction like this and we know there's an oxidizing agent, we know what the dichromate ion does. It turns into chromium 3. So look at the oxidation states. The chromium's going from 6 to 3. It's going down, it's being reduced. We've found the reduction. You have to find the oxidation. So there has to be one element whose oxidation state can go up, and that's what you have to hunt for. So here we go. Potassium's the first possibility. Potassium can either be in its elemental state where its charge is 0, or it can be +1. There's no other choice. So it can't go any higher than +1. This is not reacting. Oxygen is -2. It could go up to 0, so that's always a possibility, but because oxygen is the second most electronegative element in the periodic table, it really holds its electrons strongly, and it's very unlikely it's going to be the one that's being oxidized. So I would ignore the oxygens and see if there's any other element in there whose oxidation state can go up. That brings us to tin. Tin's charge in this reaction is +2, but tin has 4 valence electrons. It can actually go up to a charge of +4. So because of that, this is probably what the dichromate's going to react with. It's going to turn the tin 2 into tin 4. If we want to verify that by checking the last substance as well, the oxygen, it's not going to be that. But let's see what the nitrogen is. Nitrogen has a charge of +5. Nitrogen has 5 valence electrons. And the highest oxidation state per 10 charge that an atom can have is always equal to its number of valence electrons. If nitrogen lost all of its valence electrons, it would be +5. So it is already at its maximum oxidation state. It can't be the one that's oxidized. So it has to be the tin that was the only one. So the potassium's a spectator ion, the nitrate's a spectator ion, and so the predicted products would be the dichromate ion would react with the tin 2 ion to turn into chromium 3 ions and tin 4. Now, this reaction is not balanced, but we're not going to be balancing them today. We're going to save that for next time. We just want to work today on see if we can predict those products of the reaction, because that's really actually the most challenging part. Okay, next one. Let's say we are going to mix solutions of potassium permanganate and sodium iodide together, and the solution is going to be acidic. So if we have two compounds, once again, we would switch the partners. You would get potassium iodide and then sodium permanganate. Both of those are salts with alkali metal ions, so they both have to be soluble. So that means we have no precipitate, no water. It's not an obvious reaction occurring, so it must be a non-obvious reaction. And I notice one of my reactants is the permanganate ion, which is one of the strong oxidizing agents. So I'm not going to even worry about thinking about a Bronsted acid-base reaction. When I see that permanganate, this is going to be an oxidation reduction reaction, and we go to plan 9, write the reactants in ionic form. The potassium permanganate would dissociate into a potassium ion and a permanganate ion. The sodium iodide would dissociate into a sodium ion and an iodide ion. And if we want to try to predict what's going to happen, we've got to calculate the oxidation numbers. So the potassium ion's charge equals its oxidation number, that's +1. For the permanganate ion, O's are -2. The manganese works out to be +7. For sodium, its charge is +1, so its oxidation number is +1. And iodide's charge is -1, so its oxidation number is -1. So we know what the permanganate ion does in an acidic solution. It gets reduced down to manganese 2. So we found the one element whose oxidation number goes down. That's the reduction. We have to find the one that can go up. Potassium can't be any higher than +1. Sodium, just like potassium, can be 0 or +1, so that can't go up. The answer is going to be this non-metal anion, the iodide ion with a charge of -1. If it's in the presence of a strong oxidizing agent, can have its charge raised from -1 up to 0. And you can form elemental iodine, which is diatomic, happens to be solid at room temperature. So therefore, the potassium ion and the sodium ions were spectators. What's going to happen in this case is going to be the permanganate ion reacting with the iodide ion, the permanganate getting reduced to Mn2+, and the iodide being oxidized up to I2. Let's try another permanganate reaction, this time in a basic solution. Let's say we have a basic solution and we mix together potassium permanganate and sodium phosphite. Once again, it's two compounds, so we would switch the partners, potassium with phosphite, sodium with permanganate. Those are both compounds that have alkali metal ions in them, so they're both going to be soluble from our first solubility rule, so no precipitate, no water, but our reactants contain a strong oxidizing agent, so this is going to be a non-obvious oxidation reduction reaction. And the way you calculate what happens in a non-obvious reaction is you go to plan 9, you write the reactants in ionic form. The potassium and permanganate would dissociate into a potassium ion and a permanganate ion. And the sodium phosphite would actually produce 3 sodium ions and 1 phosphite ion, but I'm only going to list what the ions are, not how many. In order to figure out what's being oxidized and reduced, we actually know what's going to be reduced. It's the permanganate. So really, in order to figure out what's going to be oxidized, we have to write down or calculate the oxidation numbers of all the elements in our equation. The potassium ion's +1. In the permanganate ion, O's are -2. Manganese must be +7. The sodium ion is +1. And now for the phosphite ion, O's being more electronegative get to be -2. There are 3 of them, so 3 -2's add up to -6. So what does the phosphorus have to be? Has to be 3. So the 3 and -6 add up to the overall charge of -3. So when you're in a basic solution, you'll need to know what the permanganate gets reduced into. It gets reduced into the precipitate manganese 4 oxide. So the oxidation state of manganese is going down from 7 down to 4. So this is really what you're doing in each of these problems here. You're figuring out which one can have its oxidation state go up. Potassium can't be any higher than +1. Sodium can't be any higher than +1. Let's look at the phosphorus. If you can tell how many valence electrons phosphorus has, that's going to tell you what its highest possible charge is. So the highest oxidation state of a nonmetal is always equal to the number of valence electrons it has, because it can lose those theoretically. So phosphorus has 5 valence electrons. It could be as high as +5. So that means right now on the reactant side, this is not in its highest oxidation state. So it's going to probably go from +3 up to +5. And the way that happens is phosphite, which is an ITE ion, will change into a phosphate ion because as phosphate, if you work out the oxidation numbers, you should see the phosphorus becomes +5. So the potassium, the sodium, those are spectator ions. So the permanganate ion is getting reduced to manganese 4 oxide, and the phosphite ion is getting oxidized up into phosphate. Now, let me show you one more thing that can happen in a basic solution that sometimes slips by. If we have a basic solution of potassium permanganate and we react it with copper 1 sulfate, copper 1 sulfate Cu2SO4, because the coppers are +1, the sulfate's -2. If you just see two compounds, I would try switching the partners. That's the obvious reaction. And you would get two compounds that from the solubility rules would not predict a precipitate. So no precipitate, no water, but you do have one of the strong oxidizing agents as a reactant. So that means it's going to be a non-obvious oxidation reduction reaction. Go to plan 9. Write the reactants in ionic form. Potassium permanganate will form a potassium ion and a permanganate ion. And the copper 1 sulfate would form a couple of copper 1 ions. I'm just going to write one of them, and then a sulfate ion. So if we're going to predict the products, we're going to do the oxidation numbers. Potassium ions are +1. In the permanganate ion, O is -2, manganese is +7. The copper 1 ion has an oxidation state of +1. And in the sulfate ion, the O's are -2. They add up to -8. So the sulfur would have to be 6, so that 6 and -8 add up to -2. In a basic solution, the permanganate ion gets turned into manganese 4 oxide, so this is one product. And now we've got to figure out the other product. Potassium cannot be any higher than +1 because that's its one valence electron it loses. That's all it can do. Copper can actually be higher than +1. Copper forms either +1 or +2 ions, so this is probably the one that's going to react. It's going to probably turn into the +2 ion. Let's verify it's not something else either. Sulfur has 6 valence electrons. Its highest possible oxidation state is +6, and it's already in the +6 state, so it can't go any higher. So from deduction, copper is the only one whose charge can go up, so the copper will go up from +1 to +2. So our potassium ions and our sulfate ions are the spectators, so it's the permanganate reacting with the copper 1 to form manganese 4 oxide and copper 2 ions. Now, here's what you have to remember if a solution is basic. What species exist in a basic solution? Arrhenius is the one that told us this. Arrhenius said that the hydroxide ion is what gives solutions its basic properties. So we've just created a metal ion in a solution that has hydroxides in it. And let's think back where we heard hydroxides before. They're in one of our solubility rules. Basic solution contains hydroxide ions, and hydroxide ions from Rule 5 precipitate out of solution with all cations except those in group 1 and ammonium. So that means this copper 2 ion is going to eventually bump into a hydroxide ion. They're going to stick, and it's going to wind up forming a precipitate. So in a basic solution, you will not get free copper 2 ions floating around. They'll eventually stick to the hydroxides and precipitate out as copper 2 hydroxide. So whenever you have a basic solution, that's something to consider. If your product is a cation, cations can precipitate with hydroxides. And so think about the solubility rules before you finish your problem, because in this case, you needed to have 2 precipitates being created as your predicted products. Okay. Now, let's say we take concentrated nitric acid and we pour it onto a piece of silver. So concentrated nitric acid reacting with silver. This is actually an element with a compound. This is one of the earlier oxidation reduction reactions we learned. This is a replacement reaction. We would imagine that if you have an element in a compound, you take the elemental metal, you kick the hydrogen out, you make silver go with the nitrate, and hydrogen's released as hydrogen gas. This would seem to be an obvious reaction, except not all metals can react with acids. Acids react with every metal on the periodic table except the coinage metals, which is silver, the noble metals, and then mercury. So silver turns out not to be active enough to replace hydrogen ions from acids, so this is not an obvious reaction. These are the wrong products. So this must be a non-obvious reaction because it didn't follow along the rules of what a replacement reaction does. But we do have a strong oxidizing agent, the concentrated nitric acid, so this must be a non-obvious oxidation reduction reaction. So erase those products, they were wrong. Let's go to plan 9. Write the reactants in ionic form. Nitric acid's a strong acid because it has at least 2 more O's than H's in its formula, so that means it 100% ionizes. Elemental silver is just Ag, and we know what the nitric acid does. The nitric acid turns into NO2. That's going to be the reduction. We've got to find the oxidation, so let's do the oxidation numbers. Hydrogen's +1. The O's in the nitrate are -2 each. They add up to -6. So the nitrogen must be +5, so that 5 and -6 add up to -1. And elemental silver is 0. The product we said that I would like you to know from the list of oxidizing agents earlier, and you also find these on handout 6 as well, is the nitrogen from the nitrate turns into nitrogen dioxide. The charge goes from +5 to +4. That's going down. The only element whose oxidation state can go up is not hydrogen. It can't be any higher than losing its 1 valence electron. It's got to be a silver, and silver forms +1 ions, so you're going to get a +1 silver ion created. So the hydrogen ions are really a spectator in terms of the electron changing in this reaction. And so we'll predict the nitrate ion from the concentrated nitric acid will react with the silver to form poisonous orange NO2 gas plus silver ions. And 2 things about this. First, then in chemistry lab, whenever you're dealing with concentrated nitric acid, nobody wears jewelry because this is the only acid that will destroy that jewelry and you're never getting it back. It's going to dissolve it away. Second thing is this net ionic equation has the nitrate ion in it. And sometimes we start thinking that, oh, nitrate ions always turn into NO2. Not true. Has to come from concentrated nitric acid. Only when the solution is very, very acidic from the concentrated nitric acid will nitrate ions turn into NO2. I don't want you to think that anytime you see a nitrate as a reactant that it's going to be a strong oxidizing agent. That's not the case. So final oxidizing agent is hydrogen peroxide. Let's talk about hydrogen peroxide maybe being added to a solution of sodium oxalate. So hydrogen peroxide is H2O2, sodium oxalate, Na2C2O4. If we switch the partners, we're going to get hydrogen with oxalate, which actually makes oxalic acid, and sodium with peroxide. Neither of those are precipitates. Neither of those are water. There's no gas. And so this must be a non-obvious reaction. And we're going to have to go to plan 9, write the reactants in ionic form. And this is going to be a non-obvious oxidation reduction reaction because hydrogen peroxide is one of the strong oxidizing agents we've learned. So hydrogen peroxide, H2O2, you're going to be tempted to dissociate that into a hydrogen ion and into a peroxide ion. But it's a lot like water, it's a lot like alcohol, it's a lot like sugar. It's a covalently bonded molecule that's very stable. So remember, the only things you break apart into ions are ionic compounds, metals with nonmetals, and strong acids. And this is not a strong acid, so it does not break apart into ions. You leave it H2O2. The sodium oxalate is a soluble ionic compound that does dissociate into ions. We'll get sodium ions and oxalate ions. So if we want to predict what's happening, we've got to do the oxidation states. And in hydrogen peroxide, hydrogens are +1 each. And here's a situation where oxygen has the oxidation state of -1. It's unique, and that's why they don't call it hydrogen oxide. This is called hydrogen peroxide, meaning the oxygen has a different charge. Sodium's +1. In the oxalate ion, the O's are -2 each. They add up to -8. So the carbons must be 6. 6 and -8 would add up to -2. But because you have 2 carbons, the carbons have to be 3 each. 3 and 3 would be 6, and -2, -2, -2, -2 make -8. That's how you get the overall charge of -2. The hydrogen peroxide has a very strong tendency to turn into water. When it's doing so, the peroxide ions are going from -1 to -2. They're going down. That's the reduction. You now have to find something whose oxidation number can go up. And hydrogen can't go up, sodium can't go up, but carbon can. Carbon has 4 valence electrons, so carbon can be oxidized up to its higher charge of +4. Now, how it exists is actually not intuitively obvious. I'm doing this on paper. You're not going to get a carbon +4 ion. There are no non-metal positive ions that exist independently. So it's probably going to be some compound or polyatomic ion where carbon's in the +4 state. And there's actually 2 possible choices. It could either be the carbonate ion, so maybe oxalate turns into carbonate, or it could be the neutral gas molecule carbon dioxide, because that has carbon as the +4 state also. Experimentally, when we do this reaction, we see bubbling, so that means we know carbon dioxide is produced, so this is actually the correct product. So if carbon's ever going to be oxidized up to +4, almost always it turns into carbon dioxide. So the sodium's a spectator ion, and so the reaction is going to be hydrogen peroxide with the oxalate ion turning into water, and then carbon dioxide. And let's try one final reaction. Let's say we add a solution of hydrogen peroxide to a precipitate of zinc sulfide. So precipitate means it's a solid. We're adding hydrogen peroxide to a solid zinc sulfide. If we try to switch the partners, we're not going to get a precipitate or water, but we do recognize H2O2 as a reactant. That's one of our strong oxidizing agents. So I'm going to go directly to Plan 9, write the reactants in ionic form. So let's see, hydrogen peroxide is not a strong acid, not an ionic compound, so it just stays bonded together as a molecule. And then it said zinc sulfide was a precipitate, so that means it stays bonded together. So this is the ionic equation. Let's do the oxidation numbers. +1 and -1 in hydrogen peroxide. And then the zinc sulfide's an ionic compound from their periodic table columns. Zinc ions are always +2 and sulfide ions are always -2. So what's going to happen? The hydrogen peroxide is going to turn into water. So the oxygen is going from -1 down to -2. This is a really good one to make sure you're following along with what's happening here. We've got an element whose charge is going down, so we have to find an element whose charge can go up. So you have two choices here, okay? So can the zinc go any higher than +2? The zinc can be 0 or +2. It can't go any higher. That can't be the one that's reacting. It has to be the sulfur ion. The -2 sulfide ion can be oxidized by the hydrogen peroxide up to its elemental state of pure sulfur, which exists as S8 rings. And so this particular reaction, we wind up having hydrogen peroxide reacting with the precipitate. What it actually does, it dissolves that precipitate away, turns into water, and you actually get elemental sulfur.